So the next topic we are going to see is voltage to current converter with grounded load. So here load current is controlled by an input voltage. Once more, here the load current is controlled by an input voltage. So this is the circuit, and here V1, and here this load current is controlled by the input voltage, that is voltage to current converter. Now when you are looking into this, it is a non-inverting configurations because everything is applied to this, and here you can see that there is no supply. So the gain of output is the output voltage, okay, V0 is 1 plus RF by R1 into V1. Both RF and R1 both are equal. So V0 is 2 times V1. V0 is 2 times V1. Now we will analyze this circuit. You know that IB is 0. Now I1 is coming like this, I2 also coming like this. So IL is nothing but, when you are doing the Kirchhoff current law, current entering to a node is equal to current leaving to that node. Current entering to this node is I1 plus I2. Current leaving plus node is IL plus IB, but IB is 0. So we can write it as I1 plus I2 is equal to IL. Now what is I1? I1 is nothing but Vn minus V1 divided by R, that is I1. What about the I2? I2 is V0 minus V1 by R is equal to IL. So here, Vn minus V1 by R plus V0 by V1 by R is equal to IL. Now here you can take R as a common. So Vn minus V0, Vn plus V0 minus 2V1. This R you are taking on the right hand side, so you will getting IL into R. Now in this case, we need to find what is V1. V1 is nothing. V1 is, from this you will get it as Vn plus V0 minus ILR. So 2V1 you are taking this side and IL you are taking this side. So it will become minus ILR divided by 2. So the gain already we come across that V0 is 2 times V1. 2 times V1 means 2 will cancel. You will get it as V0 is equal to Vn plus V0 minus ILR. So here, as you can see here, yes, V0 is equal to Vn plus V0 minus ILR. Now when you are looking, this V0 will cancel. So here it becomes 0. 0 equal to Vn minus IL into R. Now, as you can see that I, we can take I, which implies that IL is equal to V naught by R. So IL is equal to Vn. IL is nothing but Vn by R. So you're getting IL is equal to Vn by R. This means that load current depends on the input voltage Vn and resistor R. That means what you want to say that here the load current is controlled by an input voltage. Okay, so that's our voltage to current converter with the grounded load. Now next topic is current to voltage converter. So here one of the most common use of the current to voltage converter is in digital to analog circuit DACs and in sensing current through the photodetectors such as photocells, photodiodes and photovoltaic cells. Photosensitive device produce a current that is proportional to an incident radiant energy or light and therefore can be used to detect the light. So that current we have to convert it into voltage. For that we are using this voltage to current converter. Now DAC using, first we will see DAC using current to voltage converter. So DAC here there are 8 inputs D1, D6, D0 to D7. Here you can see this is a DAC IC. There are 8 input. This is binary, 8 binary input. Whatever the binary input is, each binary input changes either 0 or 1. Depending upon the combination of this input, you are getting an output. Here it is, in this case it is output current, not a voltage. Now 8 digit binary signal is the input to this IC and V0 is the corresponding analog output of the current to voltage converter. So IC's output is current, but current to voltage converter converts this current to voltage. Once more I am telling, this DAC IC's output is current. That current is converted into voltage by using a current to voltage converter. See, the output of this DAC IC MC1408 is current I0, the value of which depends on the logic state 0 and 1 of the binary input and indicated by the following equation. So it can be calculated by using this equation. I0 is equal to V reference by R1, D1 by 2, D7 by 2, D6 by 4, D5 by 8, D6 by 16, D7 by 32, D2 by 64, D1 by 128, D0 by 256. I0 is, this is the general formula. I0 is output current of DAC, R1 is resistance, then V reference is reference voltage, D0 through D1, 8 binary inputs. Now you can see that when all the inputs are 0, and that time I0 is 0, and I0 is maximum when all the inputs are 1. D naught to D7R1, you are getting I naught is maximum. The I naught can be converted into desired output voltage by selecting proper value of RF. So we'll see that circuit. This is the circuit. This is this much part is completely, you can see that this is a dark, but from here onwards, whatever is there, this much part, include this capacitor, resistor and this operational amplifier, is nothing but current to voltage converter. The output of the DAC is a sinking current. That means the current is flowing inside in these directions. Now you can see that in this circuit, you can see that offset nulling configuration is there. You already know that what is this configuration. This is not about offset null. Then what happened is, when the current is in the opposite way, the output is nothing but V naught is nothing but I naught into RF. If the current is in this directions, then you can say that V naught is nothing but minus I naught into RF. Since this current is flowing towards this, is a sinking current, that is why here it is plus. V naught is V naught is plus I naught into RF. Okay, so so this is nothing but inverting amplifier, just inverting amplifier. Here it is nothing but current is coming, output will be RF into RF into the current is minus I naught into RF. So that is why you are getting I naught into RF. So in I think that in inverting amplifier, we already knows that it's already knows that ആരാത് ഞാനിവിടെ ക്ലാസ്സിലാണ്. You already aware that potential, this current is nothing but Vn. If it is Vn, then you already knows that Vn minus V naught. Now this is non-inverting, so let us assume that V1, Vn minus V1 divided by R1 is equal to, here it is V naught, V1 minus V naught divided by RF. Now V1 is 0, so Vn by R1 is equal to minus V naught by RF. Vn by R1, if you are taking as current I, Vn by R1 is equal to I. So Vn by R1 is equal to I. Then you can write it as I is equal to minus V naught divided by RF. And you can see the current direction is in this way only. Current direction is in this way. Now V naught is equal to minus I into RF. Okay, minus I into RF. Here in this case it is, in this case I naught, I instead of I naught, and I naught itself is flowing in opposite direction, so it become minus of minus I naught, so it become I naught into RF. So that's how the working of this circuit, the simple circuit. And next we will see the detecting of current through photosensitive devices. Photocells, photodiodes and photovoltaic cells gives an output current that depends on the intensity of incident radiant energy or light and is independent of the load. The current through these devices can be converted to voltage by using an, this just listen to my voice or you can see it. This current through these devices can be converted to voltage by using an I to V, current to voltage converter, and can be used as a measure of amount of light or radiant energy incident on the device. Here we will see an example in the next figure. This is perfect. This much is completely a current voltage. This is nothing but a photocell. Since it is a passive cell, it should be energized by a DC supply. When the light hitting on this, it will generate a current. The current direction is in this way, and here V naught is minus I naught into RF. Derivation I already given. So this is it. This is you can explain in your examination because you are using a photocell compared to, I think that this circuit. This is more easy to draw and explain. You are using a photocells. So it is a passive transducer. So here instead apart from photocells, photodiodes, photovoltaic cells, it will give an output current depend on the intensity of incident radiant energy or light and is independent of the load. This current we are converting into voltage by using this. Then why this capacitance is required? So it is common to parallel RF with a capacitance C to minimize overshoot and ringing. So that's completed.